Welcome back, everyone. This is our second video on acid-base chemistry, and in this video we are going to be taking a more qualitative approach to assessing the acidity of compounds relative to one another and in looking at the equilibria of a reaction. So to begin with, let's talk about how we're going to assess the strength of an acid relative to something else, and we're going to do that through looking at the stability of its conjugate base, or the ability of the base to stabilize a negative charge typically. So looking at the strength of the acid, depends on the stability of its conjugate base. So this can be done through a series of criteria that your book outlines. I'm going to go through the same order that your book, in this case, Klein Organic Chemistry, the third edition, lays out. So there are 4 criteria for assessing the stability of a conjugate base and therefore the strength of an acid. The first is the type of atom. This can be subcategorized into electronegativity, and size. The second one will be resonance. Third will be induction. And finally, hybridization of the atom, what your book will call orbitals. Okay, so we're going to go through each of these 4 criteria and look at what each of these in the list have to, well, what role they play in allowing us to assess the acidity in a quantitative manner. So let's start with number 1, the atom involved. All right, so if we take this reaction, our first question is, where does the equilibrium lie? So on the product or reactant side. And we can answer this by thinking about the pKa's of the acids. So to answer this question, we could ask, which is a stronger acid? Well, the first thing we need to do is identify which are our acids in this equilibrium. So this is an acid, and this is our acid. We're exchanging essentially this proton. All right, so if we look at our acids, we have these 2 compounds. So in order to assess which of them is a stronger acid without going to our pKa table, just to do a quick assessment of this, we can look at their conjugate bases. Okay, so now we ask the question, which one of these is happier with the charge? Which one of these molecules is more okay with having a negative charge? And to answer that, we're going to look at electronegativities. So hopefully by now you can quickly look at this and say that oxygen is more electronegative than nitrogen. So oxygen is more electronegative, which means that it's going to be more okay with that negative charge. It's going to be able to stabilize that charge better. Right? So this is going to be essentially happier with the negative charge on it, and therefore a weaker base. Because it's all right with that charge, so it doesn't necessarily need the proton. It's like, I'm okay, I can hang out here, right? Whereas the nitrogen's like, please, I want to share these electrons. I don't have the electronegativity to just hold on to this lone pair and be cool with it. So give me a proton. Right, so that would make this a weaker base. This is going to be a stronger base. What that means is this nitrogen wants the proton more. So if we go back and look at our equilibrium now, if this is a stronger base, that's going to make this a weaker acid because it doesn't want to give up that proton, because if it does give up that proton, it's going to become unhappy with that negative charge. Whereas the oxygen is like, well, I like the proton, I don't really want a charge, but I can take it, right? So this is going to be the stronger acid. And a weaker base. So this is just a quantitative view. We can say that this is a weaker base, stronger base, weaker acid, stronger acid. We therefore should be able to then identify that this is the favored side of the equilibrium, right? So we want to form the weaker acid. And we can verify our assumptions here by just looking at the pKa's. So if we look at, I'll just give this some room, the pKa of the amine, (38), pKa of an alcohol, roughly 16. So we can see that there's a very large difference in the pKa's here, and that the reactant side will be favored. The proton will sit primarily and almost exclusively on that nitrogen. So the next thing we need to discuss in the category of atom is the size of the atom. We've just discussed the electronegativity. Now we need to discuss size. So it's important to remember that a larger atom has a larger volume in which it can have the electrons shared across. So it's better able to disperse the electrons, right? to disperse the electrons, because it has a larger volume. All right, so let's take a look at what this means in terms of acidity. So, for example, we'll take this thiol plus an alkoxide, from thiolate, and so that's not a 5, that's an S minus, plus our alcohol. And we're going to ask the same question that we asked in the last example. Where does the equilibrium lie? And then to answer that, so to address this, we're going to ask the same questions that we did last time. Where does the equilibrium lie? And to address that, we're going to ask, which is a stronger acid? All right, so first we have to identify our acids. In this case, it's the thiol and the alcohol. So we're going to take a look at those. And to figure out which is a stronger acid, we're going to look at their conjugate bases. So these are our acids. Conjugate base. All right, so in this case, oxygen is more electronegative, but because sulfur has a larger volume in which to disperse the negative charge, it is going to be better able to stabilize that negative charge. All right, this means that this will be a weaker base. It's going to be okay with maintaining that charge more than the oxygen will be, which means that it's more willing to give up the proton here, which means that this will be a stronger acid than our alcohol. Okay, so weaker base, this is our stronger base. It's less happy with that negative charge than the sulfur is, which means that it's going to want the proton more than the sulfur will. Right, so then if we come back up to our equilibrium reaction, we can see that we now can identify this as our stronger acid. And therefore, the product side of this reaction will be favored. All right, we could once again confirm this with pKa's. So the pKa of a thiol is approximately like 11. I think it's 10.6 for this one in particular. And a pKa of our alcohol is, hopefully you guys remember, around 16. So this will be a product favored reaction. You can do this through the pKa numbers, or if you don't have those handy, you can just remember the trends in terms of size and electronegativity. All right, so that is the first of our criteria. That's the atom, both resonant or electronegativity and size. The next thing we're going to talk about is resonance. All right, so remember that resonance allows you to delocalize charge or spread charge a lot across a pi system. Allows for delocalization of charge. And the more spread out it is, the more stable it is. So we'll take one more example of this. So if we're looking at a reaction of a carboxylic acid with an alkoxide, forming our carboxylate and our alcohol. All right, we're going to ask the same questions that we did in the previous ones. Where is the equilibrium? Which side is favored? Which is the stronger acid? Well, first let's identify our acids. We have a proton here, and our proton ends up being there. So our acids in this case are our carboxylic acid and our alcohol. These are our acids. Now, to identify which one is stronger, let's look at our conjugate bases. All right, so in this case, both of our atoms both atoms that contain the charge are oxygen. So we don't have any atom effects. It's both size and electronegativity are equal in this one. But now we can look at resonance, because this compound, our carboxylate, has the ability to share that negative charge with the other oxygen. So this one delocalizes the charge across two oxygens, whereas this alcohol or alkoxide is stuck with the negative charge on one oxygen. And therefore, because this one can share the electron density of that negative charge, or share the negative charge with another atom, it's going to be more delocalized and more stable. And therefore, our weaker base. Right? So it's okay with maintaining that charge much more than our alcohol is. If that's our weaker base, that means that this is our stronger acid. So that means if we come back up to our equilibrium, if this is our stronger acid, this side will be favored. And therefore, you will have more of the protonated carboxylate or protonated alcohol and the formation of our carboxylate. So most of the atoms will sit, so the alcohol and the carboxylate in this solution. We can again confirm this with pKa's. I'll let you go ahead and do that one, just so you are familiar with the pKa tables. Now that we've reached two of our criteria, that being atom and resonance, we're going to look at our third criteria, which is induction. So number 3 on this list is induction. right? So induction is the sharing of electrons or of electron density through our sigma bonds. So resonance is delocalization of charge through the pi bonds. As we define it for this course, induction is the sharing of electrons through sigma bonds, and this occurs because of changes in electronegativity in the attached atoms. I'll show you an example of that here. So if we have two alcohols, and one of them contains a trifluoromethyl group, oh, and it doesn't help that these are both, okay. We're again going to ask the same question we've asked in the previous examples. Which side of this reaction is favored? Where does the equilibrium lie? And therefore, which is a stronger acid? Right? So first we start by looking at our acids. So in this case, we're going to identify our alcohols as our acids. Then draw our conjugate bases. All right, and then we have to ask the question, which of these is better able at stabilizing the negative charge? And I'm going to draw this out just so we can identify some of the forces at play here. So one of the things to remember is fluorine is highly electronegative. So it's going to pull electron density away from this carbon. And as a result, it's going to pull electron density away from the carbon attached to the oxygen, which means that this oxygen is going to be able to share electron density into this slightly more electropositive carbon through the sigma bonding system. So this will allow for the slight dispersion of electrons through the sigma system better than this. So we can create a dipole which pulls electron density away from the carbon-oxygen bond and towards the fluorines. So therefore, this is better able to stabilize the charge, and this will be a weaker base, which makes this our stronger acid. All right, so if we come back up to our equilibrium, this is our stronger acid. Therefore, this side will be favored. All right, so the last of the four criteria we have for qualitatively assessing the relative acidities of different protons is hybridization or orbitals. So your book will refer to this as orbitals, but what we're dealing with is the hybridization on different atoms. So in organic chemistry, we're typically dealing with compounds that have one of three hybridization states. That's either sp3, sp2, or sp. So we're going to take a second to look at those orbitals and how their shape can influence the acidity of a proton. All right, so if we look at our sp3 orbital, remember that this has the most p character. The electrons are able to sit further away from the nucleus because they're in a more p-like orbital. As we move towards sp, remember we're getting more s character than we do in sp3 or sp2. The atoms are, or the electrons are going to sit closer to the nucleus of the atom. So these electrons are going to be closer to the nucleus. Which means that they are going to interact more closely with the positive charges of the nucleus and therefore be slightly more stabilized, right? Keeping in mind that the nucleus is positively charged. So this allows us to stabilize negative charges in sp orbitals more than in sp3 orbitals. Okay, so let's take a look at an example of this. We're going to frame this question a little differently than we have the others, just to give you some other examples of things that you should be considering or thinking about when looking at pKa's and thinking about acidity. So I'm going to draw out all of the protons on this compound. We're going to ask which proton or which carbon will be deprotonated first. Which is just another way of asking which is the most acidic carbon or most acidic proton. All right, so we can look at this in several ways. And I guess one of the easiest way, and for the sake of right now, we're going to treat all of these sp2 hydrogens as equal. They're not exactly because they're attached to different numbers of carbons, but for the sake of this example, let's just group these into sp2, so our sp2 carbons with protons, our sp hybridized carbon with a proton, and then we'll group these as the protons on sp3 carbons. All right, so if we deprotonate one of our sp2, we're going to end up with a lone pair that is perpendicular to the pi system, right? So when we draw this, and I guess another way of drawing it would be just to make this a little easier. This is how it would conventionally look. This lone pair is not part of our pi system of the double bond. This is perpendicular to that, so it's in its own p orbital adjacent to that. All right. The same with if we deprotonate our blue proton on our sp hybridized system. And let's draw these in. So again, this lone pair is not part of the triple bond. If we were to draw the triple bond out, we would end up with this carbon also having a lone pair sitting perpendicular to the p orbitals, keeping in mind that, you know, all of our p orbitals are going to sit something like that. And this one's going to sit outside the plane of these two pi bonds. So it's not involved in this triple bond. It's not capable of being involved in resonance. It's just in its own orbital. All right. And then finally, the other option is to remove one of the hydrogens on our methyl groups. Now, these two methyl groups are equivalent, so it doesn't matter which one we're looking at. So if we're looking at each of these, we see that this lone pair sitting here was part of an sp3 hybridized carbon and is now sp2. This one is going to sit closest to the nucleus. So this is going to be furthest from the nucleus. This one will be closest. And therefore this one will be the most stabilized by the positive charge of the nucleus and will therefore be the weakest base. And this will therefore be the most acidic position. So if we look at these in terms of pKa's, this one will have a pKa of roughly 25 for an sp hybridized proton. For sp2 type systems, and while these won't be exactly equivalent, the pKa's approximately 44. These are in the 50s. So this, again, most likely to be deprotonated. So if you were going to add a base, this is what you would form. Okay, so that's how we think about hybridization effects. The more S character your carbon has, the more likely it is to be deprotonated because it can stabilize that negative charge. One thing to keep in mind here is, however, notice that even the most acidic of protons is still not a strong acid. It's still a weak acid. These are not protons that are easily going to go away. You're going to need a relatively strong base in order to remove any proton from a carbon. Okay. With that, that's our qualitative approach to pKa's assessment and relative acidity assessment. And next up, we'll be talking about functional groups and their characteristics.